Welcome to The Explainer. Okay, so have you ever really thought about how your calculator knows that 2 plus 2 is 4? Or how your computer can remember your password, like, instantly? Well, the magic behind all of that is something called special logic circuits. And today, we're going to break them all down piece by piece so you are totally ready for your digital electronics exam. All right, let's start with the big picture here. The absolute best way to think about these circuits is to imagine them as digital Lego bricks. Seriously. Each little brick has a really simple, unique job. But when you start snapping them together, that's when you can build these incredible things, like the calculator we just talked about, or even the memory inside your computer. So, here's our game plan. We'll kick things off with the exclusive gates. Then we'll see how those build circuits that can calculate things, and then circuits that can actually remember stuff. After that, we'll get into counters and registers, and we'll wrap it all up with a final exam review to tie it all together. All right, first up, the exclusive gates. These are really the fundamental building blocks for comparison. Okay, so let's meet our first Lego brick, the XOR gate. Now, its whole job, its entire reason for being, is to be a difference detector. It's super simple. If the two things you feed into it are different, say a 1 and a 0, it shouts out a 1. But if they're the same, like two zeros or two ones, the output is just a 0. That's it. That's the rule. And here you can see exactly how that works. This truth table is basically the cheat sheet for the XOR gate. Just look. See how the output is a 1 only in those middle two rows where the inputs are different? That's the difference detector in action. And this simple function, believe it or not, is absolutely essential for building the circuits that do math, which is exactly where we're headed next. So section 2, circuits that calculate. Now we get to the fun part, how computers actually do math. So we've got this difference detector gate, but how do we go from that to a circuit that can actually add numbers? Well, that brings us to something called an adder. And here's our first one. This is a half adder. It uses that XOR gate we just talked about to calculate the sum of two bits. But crucially, it also gives us a carry output. This is exactly like when you're in grade school doing addition and you had to carry the 1 over to the next column. Same idea, just in binary. Okay, now this is where that Lego idea really clicks into place. This is a full adder, and it's literally built using 2 of the half adders we just saw. But its superpower, the thing that makes it so important, is that it has a carry-in input. So not only can it carry a 1 out, it can also accept a 1 carried in from the previous column. And why does that carry-in matter so much? Because it lets us chain them together. When you connect a bunch of full adders in parallel like this, you suddenly have a circuit that can add numbers of any length, not just single bits. This is the core of an arithmetic logic unit, the ALU, which is basically the number-crunching brain inside a computer processor. Okay, next section, circuits that remember. It's great that circuits can calculate, but what good is that if they can't store the answers? How do they remember information? Well, for that, we need a totally different kind of Lego brick called a flip-flop. So what is a flip-flop? Well, it's the most basic form of computer memory you can get. The best way to think of it is like a light switch. It has 2 stable states, right? On or off. We use those 2 states to represent a single binary digit, a 1 or a 0. It just sits there holding on to that one tiny piece of information. Now, there are a few different kinds of flip-flops, but if you're studying for an exam, the JK flip-flop is the one you really need to remember. Why? Because it's like the Swiss Army knife of flip-flops. You can configure it to act like any of the other types, which makes it super versatile. And here's a great little study aid for you. This table breaks down the main types of flip-flops and what their primary job is. You've got the basic RS, the D for data, the T for toggle, and of course, the versatile JK. The key takeaway here, the big idea, is that they all in some way are designed to store or manipulate a single bit of data. Okay, let's keep building. Section 4, counters and registers. So we now have a way to store a single bit using a flip-flop. The logical next question is, what happens when we group a bunch of them together to organize and store bigger chunks of data? Well, one thing you can do is chain them together in a series, and when you do that, you get a counter. Just like the name says, it counts things. Specifically, it counts events like clock pulses. This is so fundamental. It's used for everything from the timing operations in a processor to keeping track of what step a program is on. But what if you group them in parallel instead of in a chain? Then you get something different, a register. Now, a register lets you store a whole chunk of data, like an 8-bit number, all at once. The best way to think of it is as a temporary scratch pad for the computer's processor. It holds on to data right before it's about to be used. All right, we have covered a ton of ground. We've gone from simple gates all the way up to circuits that can count and store data. So let's do a quick fire review just to lock in these key concepts and make sure you're feeling good about them. Okay, remember these 5 core concepts. It all starts with the XOR gate for comparison. That lets us build a full adder for doing math. Then we have the flip-flop, which is our basic unit for memory. We chain those together to make a counter for counting events, or we group them in parallel to make a register for storing data. See how it all builds? All right, time to test yourself. First up, what type of adder do you need to handle a carry from a previous circuit? You know, the one that lets you do multi-digit addition. And the answer is the full adder. Yep, that carry-in input is the essential feature that makes it all work. Okay, next one. What's the most versatile type of flip-flop? Remember that Swiss Army knife we talked about? That would be the JK flip-flop. Exactly. Its versatility is what makes it such a go-to component in digital design. And for our last question, what's the general name for a circuit that's made of a group of flip-flops and is used for temporary data storage? And that is a register. You got it. And really, that's the whole point, isn't it? The whole idea is that these simple little building blocks, these digital Legos, they all combine to create the powerful processing and memory that we totally rely on every single day.